This is the second video for the 14.7 session on filters, and I will give you an example of a low-pass filter. There's no set low-pass in general, except that this is absolutely the most traditional one, is on RC. I gave you an example last week of how to do the transfer function of V out over V in, and we did a voltage division, so it's the voltage across the capacitor divided by or it's the impedance of the capacitor divided by R plus the impedance of the capacitor, and you end up having an H of S like this. What happens is that this is going to be the corner frequency, so 1 over RC is in radians per second, is the frequency at which you're going to start to see the decrease. That's the pole, basically. So if you see my previous video on how to draw a Bode plot based on a transfer function, you're going to see there is a maybe there's a gain here, but then at that omega c of 1 over RC, this will start going down at minus 20 dB per decade. And this is a traditional gain profile in a Bode plot for a low pass passive. So passive filters only have resistors, inductors, and capacitors. Later we're going to see how to design active filters with op amps. For now, I'm going to give you an example of a low-pass filter that's less common, which is an RL. I also think it's much less common to find filters like this, let me see, in many lower frequencies, so it's more common for RF, I guess, that you do have to take into account inductances of the lines of what you're doing. So here, when I find the transfer function again, it's going to be V out over V in. And I will say that that's also a voltage division, so it's the resistance divided by the impedance added of the two, the resistance plus j omega L. Instead of this, you could have written SL also. I'm going to divide everybody by R. So both sides plus j omega L over C. And this is basically the transfer function. And you see the L over R. Yes, I still have brain problems here. You see that the cutoff frequency, which is 2 pi f, will be R over L. So when this omega is R over L, then we have this equals 1. So basically the do I want this? Oopsie. I should have done this. So that's a transfer function. So basically, because there is only a pole here, the same kind of graph is true. That it goes all the way to omega c, which is R over L. Then it starts decreasing, the gain starts decreasing by 20 dBs per decade. Gain in dB. And this is omega in radians per second. So next we're going to take a look how to design one of these circuits under some constraints.